Hello everyone, welcome to Chemazon-Complete Chemistry. In today's video, we are going to learn some of the very important terminologies that are related to infrared spectroscopy or IR spectroscopy. So these are the terms that we are going to see. What is infrared spectrum, percentage transmittance, functional group region, fingerprint region, what is intensity of the IR peaks, stretching and bending modes. And this is how an infrared spectrum looks like that we are going to see in detail. So, first of all, let us try to understand what is a basic principle that is involved in infrared spectroscopy. So, we know what happens is vibration of the bonds. But when does this vibration takes place? The basic principle is absorption. So, what is the key principle? Absorption of the IR. IR is the infrared radiation. Okay, infrared radiations are absorbed. That is why this spectroscopy is also called as infrared or IR spectroscopy. Okay, so when does this take place? Suppose I have any one particular bond, let's say carbonyl group. Now carbonyl group has a fixed frequency, stretching frequency, that is 1700 centimeter inverse. So this carbonyl bond will its stretching frequency is 1700 centimeter inverse. So when will absorption take place? When I incident infrared radiations, okay, IR radiations, and this IR radiation frequency of this IR radiation should also be same, that is 1700. When both these frequencies match, what will happen? Absorption will take place. Okay, the bond will absorb IR radiation, and due to which what will happen? Either the bond will stretch, that is stretching mode of vibration, or the bond will bend, that is bending mode of vibration. And in the IR spectrum you will see a quantity, physical quantity called as percentage T, which gives us the amount of percentage transmittance. Okay, it gives the percentage transmittance. Now what is this percentage transmittance? We will see in the moment. So the basic principle here is absorption. So it is the peaks that we see are for what? Are for absorption of the IR radiations. Okay, so now let us see how exactly this works. Okay, so this intensity of peaks we will see in a moment. So this is a molecule, this is ethanol molecule, CH3CH2OH. Now you can see in this animation, as each bond vibrates, you will see that you get an inverted peak. So first let us see this again. So OH, as OH bond vibrates, you can see we got a peak for OH. Then as CH bond vibrates, we get the peak for CH. And then at the end CO bond vibrates, we get the peak for CO. So this is OH, then CH bond vibrate, and then carbon oxygen bond vibrates, and we get the peaks in the infrared spectrum, as you can see here. So this is a plot of what? This is a plot of percentage transmittance versus stretching frequency. Okay, now the question is why these peaks are inverted, that we'll see in a moment. Okay, so what exactly is infrared spectrum? It is plot of percentage transmittance versus the stretching frequency in centimeter inverse. So now if you see in an infrared spectrum, there are two basic regions. Okay, there are two basic regions that are present in an infrared spectrum. One is called as a fingerprint region. Okay, and there is another region that is called as functional group region or functional region. Okay, so what exactly is the meaning of fingerprint region? So the literal meaning of fingerprint, we know every human individual, we have different fingerprint that is specific to one particular individual. Now I will be having one particular fingerprint, and you will be having another completely different fingerprint. Just like this fingerprint is an identity of a particular person, similarly fingerprint region in infrared spectrum will be different for all the molecules. Okay, any two different molecules you take, the fingerprint region will be completely different. And the other region is functional group region. So there are two regions you can see here. One is the fingerprint region, which ranges from 600, okay, 400 or 600 to 1400, roughly from 600 centimeter inverse, or we can say 400 to 600. It starts from 400 to 600 centimeter inverse and ends at 1400 centimeter inverse. So this region is called as a fingerprint region, and it is unique for all the molecules. Any two different molecules you take, you will get different regions. And another region is the functional group region. This is very important region that we are going to see, that will be helpful for us to analyze the molecules, the organic molecules. So this is the functional group region that you can see from 1400 to 4000. Okay, here whatever peaks that we see, that will be important to identify the functional groups. Okay, that will be helpful to identifying the functional groups. So now there is one question. Suppose there are two molecules which have same functional group, let's say alcohol. So will they have the complete spectrum will be same, complete infrared spectrum will be same? So the answer is no. So you can see here there are two different molecules. This is what 1, 2, 3, 4, 5. Pentane 2-ol. Okay, pent means 5 carbon chain, second position there is alcohol, and this is pentane 3-ol or 3-pentanol. Okay, so these are what functional isomers. The position of these are position isomers. The position of the functional group is different. Okay, these are what position isomers. So now here you can see the functional group region, which is shaded lightly dark, as you can see here. From here to here, this region is the functional group. Specific for the functional group, you can see this peak is almost same. Why? Because the functional group is same, that is OH, that is alcohol. But if you see the fingerprint region, that is from this 600 to 1400, this you can see it is completely different for both the molecules. Either they, okay, although they are what, they are isomers. Okay, they are isomers, still their fingerprint region is what, fingerprint region is completely different. So in this way, any two different compounds that you take, the fingerprint region is going to be completely different, even though functional group region can be same because the functional group is same. Okay, so now the question is, why the peaks that we seen just now in the previous slide, they were inverted. But what we are studying is the absorption, right? So if you see the absorbance spectrum, it is something like this. Peaks are straight like this. Okay, that is the maxima you can see like this. Okay, this represents the absorbance. Now if you see the relation between absorbance and percentage transmittance, what you will see is that absorbance is minus log of percentage transmittance. So what we are calculating exactly is the percentage transmittance. As you can see here, what we are calculating is the percentage transmittance. Now what is the meaning of this percentage transmittance? So suppose for this peak you can see here, this is what 60 approximately, this is 60%, 60 percentage transmittance. So what exactly we are seeing is, suppose I take any sample. Okay, initially there is 100% intensity. Okay, some amount X will be absorbed. Okay, and the remaining part, this is what this is called as a transmitted light or transmitted radiation. This is what we measure in an infrared, in the machine that is called as infrared spectrophotometer. Okay, infrared spectrophotometer. Okay, in IR spectrophotometer, what we measure is the transmitted radiation, that is nothing but called as percentage T or percentage transmittance. Okay, so if you see the relation between absorbance and percentage transmittance, it is minus log of percentage T. Okay, so I'll give you one exercise. What you have to do is, one is this percentage transmittance 60%, and another is the percentage transmittance of 0. As you can see here, for this peak at 1700 for carbonyl group, this is what, this is approximately 0. So what I want you to do is, you have to calculate the absorbance for both the percentage. One is for 60% transmittance and another is for 0% transmittance. So what you will find that the percentage transmittance for 0% transmitted light, that is what, that is almost all of the light is absorbed. Okay, so almost all of the light is absorbed, that you can see. You will, when you calculate, you will come to know that for this peak, for carbonyl, you will find that the absorbance is, for this peak, is going to be greater as compared to the absorbance, where the percentage transmittance is what, 60%. Okay, so what exactly we are seeing is nothing but the absorption peaks. Okay, absorption peaks. Okay, 100% transmittance means there is no absorption. Okay, no absorption that is taking place. And when we see the inverted peaks, when there will be some absorption that is taking place. The intensity of peak depends on what, that we will see in the next slide. I hope you have understood that as the intensity or deeper is the peak, that is what, that is called as a strong transition, that we will see in a moment. And what does this intensity depend on, that we will see now. So why these peaks are inverted? Because we are seeing the transmission. Okay, we are not seeing absorption. If we are seeing absorption, as you saw here, we will get a normal peaks that we see in the graph. They are not inverted. Okay, so now the question is, what does the intensity of the peaks or depth of the peaks depend on? So you had seen some are weak transition, some are medium, and some are very strong transition or strong absorption. So this intensity of the peaks, it depends on what? It depends on the change in the dipole moment. A change in the dipole moment of the bond during vibration. Change in the dipole moment of the bond during vibration. Okay, now what does this mean? And what does this depend on? This depend on the polarity of the bond. Okay, and polarity, we know it depends on what? It depends on the electronegativity difference of the bond. Electronegativity difference of the bond. Okay, so what is the meaning of that? Suppose I have one CH bond, which is, we know it is non-polar. Okay, or we can see it is very slightly polar. Okay, this is less polar as compared to, let's say I take carbonyl group. So what will happen if I incident, okay, suppose I incident infrared radiations here, there will be very slight change in the bond length like this. Okay, let's say we are doing stretching. Okay, we are doing stretching. Then you can see this is symmetric stretching. So you can see there will be very slight change in the bond length. That is, a change in the dipole moment is going to be less. Okay, but dipole moment, what does dipole moment depend on? Mu, dipole moment depend on the charge into intermolecular distance, that is the bond length. Okay, so the bond length, change in the bond length is very less. So the dipole moment is less. Dipole moment is less, so polarity is less. That means what? Intensity will be lower. And same if we see for carbonyl group, suppose carbonyl group are incident with infrared radiation, you will see that the change in bond length is much higher. Okay, is much higher as compared to that of the non-polar bond or less polar bond like CH. So for CH, you will see what? You will see a weak transmission. Okay, that is very less amount of light is absorbed. Whereas for carbonyl, you will see that the absorption is very high. That is very less percentage transmittance. So in this graph, it is very clear. You can see for CH bond, the percentage transmittance is what? It is very less. That is, it is very high. Percentage transmittance is very high. Let's say this is 78. Okay, this is high. Percentage transmittance is high. That means low absorption. And for carbonyl, you can see it is, the intensity is very high. That is, the percentage transmittance, you can see it is very low. Let's say this is 10%. So this is very high absorption. So the carbonyl is what? It is going to give very high absorption and very less percentage transmittance. So now at the end, we have to see what are the different types of molecular vibrations. Okay, they are of two types we had seen in the last video. If you have not watched that video, I will provide the link in the description. One is the stretching mode of vibration, another is bending mode of vibration. So in stretching, what happens is there is change in the bond length of the bond that is vibrating. In bending, what happens is it does not occur along the line of the bond. So in a bending vibration, what changes is the bond angle. In stretching mode, what changes is the bond length. Okay, and they are of two types. One is stretching mode of vibration, another is bending mode of vibration. Now in stretching modes, we had seen in the last video, one is symmetric stretching, another is asymmetric stretching. And in bending also, there are two types of bending modes. One is in plane bending modes of vibration, another is out of plane modes of vibration, bending modes of vibration. In plane, they are of two types. One is scissoring, another is rocking, and out of plane bending, they are of two types, wagging and twisting. So we had seen in detail what is the meaning of these modes of vibration. You can see that video if you have not watched that. And this is the end of this video. I hope you have understood all the different concepts. What is the basic principle of infrared spectroscopy, why the peaks are inverted, and why do we get inverted peaks? That is because of the percentage transmittance that we are measuring. That is a transmitted light we are measuring. We are not measuring the absorption, or we are not measuring the absorbance. Okay, and what does the intensity depend on? Intensity of the bond depends on its polarity. Okay, more is the polarity of the bond, more will be the change in dipole moment. That is, more will be the intensity, that is the depth of the peaks will be higher. As we had seen in carbonyl, as we had seen in carbonyl, the intensity was higher, as compared to CH bond it was lower. And these are the types of molecular vibrations. Thank you.